So now in this video, we come back to a circuit I did in the last video. Now, we have a 4001 integrated circuit right here. What that means is there's 4 NOR gates. We're using the bottom left one. You have to power it, top right, and then bottom left are the power pins, so positive, negative. You should not leave the inputs of the other NOR gates floating. You should give them a voltage, but we'll be alright. For demonstration purposes, it reduces clutter, makes it easier to see what's going on. And I realize I'm kind of far back. We don't need to be. We don't need to look at the multimeter right now. So, any case, trim pot, we can set a high or low signal like that. When it comes to the light dependent resistor, it's a voltage divider, but we have an override switch. So I'm going to dim the lamp. There you can see at that lighting level. Now that input is high, low, I mean. We have a connection to ground with the resistor. The light dependent resistor is not conducting as well, so it's to the positive supply, and therefore it's not conducting as well. That pulls the voltage down. If I turn the trim pot up, so you can see the voltage range with the trim pot right there, somewhere about halfway. High enough, we get a high input, a low output. If any input is high, the output will be low. So it's the opposite of an OR gate. An OR gate is when any high input equals a high output. They all have to be low for the output to be low. Now we have the opposite. So now we got them both low. That LED is lit up. But again, I have the override switch. So the purpose of this video is that we have a 1000 ohm resistor protecting the red LED and the blue LED. And if I turn the lamp up, you know, it's kind of hard to see that the red LED is lit. I would rather use a 220 ohm resistor, but I don't even think we're going to get the full supply voltage out. So we have 5 volts at the supply. You know, it's a little bit lower. We got some losses and stuff. Maybe the power supply doesn't exactly output 5 volts. But there you can see output is low right now. It's about 0.531 volts. So it should be 0 volts, and this output should go rail to rail, but we're powering a load. There you can see I removed the load. We got 0 volts at the output. I'll put the LED back right there. So we are really limited with the current on this, especially at 5 volts with the supply. So I'm going to go low and go low right there. There you can see 4 volts out of that 5. We expect 5 volts with this integrated circuit at the output. I yanked the LED. There you can see now we got it. You know, it'll be, you know, like thousandths of a volt off, but it's practically the full supply voltage. Now I return the LED, and we got 4. So the data sheet says we can only expect about 0.88 milliamps of current being synced or sourced when the supply voltage is 5 volts. Now, you can also do 10 volts. You can do up to 15, but we'll just do 10. And I think I should use higher value resistors for 15 volts. But any case, we'll go to 10. So now you can see when it comes to the low input, we're about a volt. So like twice as bad as it was before off. And then now we're falling less than a volt and a half below 10 volts right there for the high output. But if we remove the LEDs again, so there you can see practically 0 volts. Not as good as it was with 5 volts, but again we have twice the voltage. So you know we got, instead of like 6 thousandths off, we have like 12 thousandths off. And there you go. So out of 10 volts, we got like 9.95, and remember the supply voltage doesn't seem to get as high. So yeah, it looks like we have the total positive coming out that we have at the supply, because we're not quite getting 10 volts at the supply. And interesting, looks like it's a little bit higher for some reason. So maybe there's like a little more resistance along the way over there or something that's kind of making it lower over there than what we're getting with the integrated circuit. But any case, there you can see we can output the full supply voltage, but not while powering a load. It's really limited to how much load it can provide, and according to a data sheet I looked at a long time ago, At 10 volts, we can sync or source about, is that 2 or 3? 2.25 milliamps of current. Whereas at 5 volts, we could only sync or source 0.88 milliamps of current. So we can get about 3 times as much current if we double the supply voltage from 5 volts to 10 volts. Hopefully that makes sense. So, any case, yeah, when you look at data sheets and stuff, it's good to take actual voltage measurements anytime that it mentions like voltage and how it can affect the integrated circuit right there. So I thought I would make kind of this bonus video right there. Again, it's a NOR gate. We need all inputs low. So trim pot down to a low enough setting and you cover this. Maybe you want a light sensitive circuit right there, but you don't want it to operate all the time. Maybe you want it low at certain times, no matter, or yeah, the output low no matter what. In that case, you can just turn the trim pot to higher, and then when you want it so that the output goes high when it gets dark enough, then you can put the trim pot to low, and then when you cover the trim pot, or the light dependent resistor, that's when we had the red LED lit. So, you know, the OR gate could be used so that you can disable when a sensor affects the output. Hopefully that makes sense. So, in any case, that's it for this video. Hope you enjoyed. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.